Hey everybody, we are getting down to the last lesson, or the second to last actual math lesson. We'll see how much I get done in this 15 minutes, but I wanted to talk about the math behind, or some of the math behind that video you saw. There's so much math. It's one of my favorite topics. In fact, you just could go on and on and on, but it's really like it's geometry intersected with Algebra 2, and hopefully you get to study more of it in Algebra 2. I know you're excited. But I wanted to talk about, if I were going to design an elliptical pool table, how would I draw it? How would I figure out where everything goes? And the big question you need to figure out is first the shape you want to make it. So I made this drawing, right? Probably could have drawn it a little better. This probably is a little bit too squished, but the idea is it's kind of like a squishy circle. You take a circle and you kind of stretch it out like that. And instead of a center for the circle, there's a center for this, it's almost like there's two centers, and they're called focal points, or foci. Those will go here and here somewhere. And those points turn out to be the points where you want, one of them is where the hole goes in your pool table, and the other one is where you want to shoot the ball from. And so you really need to find that point. So we're going to get to that in a minute. First, I wanted to do a little bit more about, so you get a little bit better picture than this. Let's see. So here we have a squishy circle, and it's actually a circle. So I've got these values here which are kind of weird, but a equals 1 and b equals 1, those are important. If they're both equal to 1, then your equation up here is x squared over a squared plus y squared over b squared equals 1. That's just x squared plus y squared equals the 1. It's the equation of this little circle you see in the middle. Well, if I change these values, I could make the circle bigger. So I could change a to 2, or let's make it even bigger, a to 10. So what did I do? Well, I stretched it out so that on the x-axis I go between negative 10 and positive 10, but the y-axis I go between negative 1 and positive 1. So if I stretch it to b is 5 and a is 10, I get that. If I make b 5 and a 6, let's see if I can get that, there we go. That's what I was trying to draw on the chalkboard. So basically, just changing those values, the a and the b, stretch your circle out. That's one important thing to know. It's the equation of a circle, but squished. And those a and b values are important. If we go to this view right here, this is from the thing I pushed out to you with the notes and the problems. The other thing I wanted you to be able to do is just to learn really how you're supposed to read a textbook. So this is the information at the beginning. It's really important information. All this stuff here, graphing equations of ellipses, you really want to read through that and read through it again. I'm doing a graph of an ellipse that's on its side like this, but if you notice on each of these quick pictures, the vertex is the one where it's longer. So the vertex is a0 and negative a0. There's two vertex. It's the same with the one that's vertical also. But study that. Really spend some time studying that and looking at the examples. I'm going to do an example similar to this one, except for this one they just found the equation. So similar to example 2, but I'm going to find the equation and I'm going to find where those points are. So let's go back to the picture here. So I want to find the equation, and my equation is just y, x squared over a squared plus y squared over b squared equals 1. If you looked in the book, or the paper I pushed out, the notes, sometimes they put b squared here and a squared here. Well, that depends on whether it's vertical or horizontal. This is horizontal, so it's longer this way, which means I'm going to put the a underneath the x. So the a is always the long one. This is your vertex. Your vertex is 6, 0. And this is your other vertex. -6, 0. And this up here is called a co-vertex. And it is 0, 5. But then here's another co-vertex. It is 0, -5. So you have all your vertices, co-vertices. That's enough to to get the equation right there. Put all this information, and my equation becomes x squared over a squared. A is 6. So 6 squared plus y squared over b is 5. So 5 squared. So there's my equation. Then I could square those things, and I get x squared over 36 plus y squared over 25 is 1. Now, the cool thing about the elliptical pool table, and the thing we need to understand, is that you have these 2 points here that are called foci. And the idea is one of those points is the hole where the ball goes into. The other point is where you shoot the ball from. And if you shoot the ball from that point, it'll go into that hole every time. It'll go up here and bounce to that hole, or go here and bounce straight to that hole. And it's because in any one of these ellipses, those two values are a constant. So I'm going to go back to, let's see if let me show it here. I'm going to go back to this picture. And you can see that the way they draw, oh yeah, this drawing up here, the focus, D1 and D2, that means, the way they say that is that the ellipse is the set of all points P in a plane such that the sum of the distances between P and two fixed points called the foci is a constant. That means D1 plus D2, no matter where you are on the ellipse, are always going to be equal to the same thing. It actually turns out to be 2a. Well, that is what gives us the property that makes the pool table work. So up here, what I want to do is I want to find those 2 points, because I want to be able to find, you know, I'm going to use this formula up here for that. That formula, bring it down here, and I know A and I know B now, and I'm going to find C. So C squared is A squared minus B squared. Looks like the Pythagorean theorem, but it's not quite. I'm going to do, so you always want to do the large one minus the smallest one. So A is always the largest one, 6. So 6 squared minus 5 squared, which is 36 minus 25, which is 11. So C squared equals 11. C is equal to the square root of 11. Now, the square root of 11 is, let's see, what is that? I should calculate that really quick. I didn't bring a calculator with me today. I can find that. Again, if I go to let's just get a calculator. Or just Google square root of 11. Will that work? We need Carmina in the classroom to ask Siri. Square root of 11 is 3.32. So about 3.3. Okay. So square root of 11 is about 3.3. Plus or minus when you take the square root, right? So it's plus or minus the square root of 11. That's good because we have two values. 3.3 and negative 3.3. If you were to really build this thing, you would just make this hole large enough to cover it, because these are approximations of the decimals, right? So let's say you put your hole here, you're going to shoot there, and this is where the ball starts. Well, it just means that no matter where I shoot from, I could shoot from here, and it's going to bounce off the wall at the exact same angle, and it's going to shoot and get right into the hole every time. So I could go from here to here. It'll go right in every time. That's the property here. Okay, so it's always going to hit there. We found how to build this thing where it is. The only other interesting thing would be if you really build it, what materials do you use? I think you could build it nicely out of cardboard. Probably wouldn't last forever, but cardboard and maybe you need some kind of rubber material, like that you could put, like maybe even pool noodles. It's not really rubber, but you might be able to put those around it. You could actually build this. So I'll let you guys decide if you're going to actually build one and take a video of you shooting the pool. You could use a ruler as the pool stick. See how far you want to go with this, or you could just design it. That is that's the mathematics of it. And you need to be able to get that down. That's got to go into your design. And I want to show you one more cool thing before we finish. And it's this. So right here, here's an elliptical billiard table, and there's this problem in mathematics, which is, I think it comes from Euler. I should look it up, and I was going to work on it, but I still haven't done it. But the idea is, it says an elliptical billiard table, the envelope of a trajectory is a smaller ellipse, a hyperbola, a line, whatever. Let's just play it. So the ball is being shot, so the two squares on the side are the foci. The ball is being shot from somewhere where it's not on the foci. Okay, so I'm going to play it, and you're going to see. Let me crank up this velocity here. And you can see this trajectory. I'm going to go faster. So you shoot the ball. It's never going to go into the hole. Can't go into the hole. Because it doesn't ever, the only way for it to go to the hole is if it hits that foci on the left, the focus point on the left, and then it'll shoot up into the hole. So you always have to, whatever you're aiming for, has to hit that focal point in order to get the ball into the hole. That's the key. And you end up with a picture like this, which is actually a different kind of conic section called a hyperbola with a similar kind of an equation, which I'm not sure we're going to have time to work on today. But I wanted to show you guys that stuff, and I wanted you to see it all and maybe take some notes on it. So go ahead and take notes on this, and then you're going to design your own pool table. And when you do, I'm sure it's going to be amazing. And we're all going to have something to rejoice about at the end of the school year. Have a good day.